Okay, well, without further ado, let's start today, right? Everybody's here. Reminder for what we discussed last week. Okay, so the first lecture last week, we talked about this very simple problem. If we have a y and we have an x, and suppose we have a bunch of data points. Now, in order to use x to predict y, I need to what? I need to find EY given x. Right? EY given x is the best predictor of y based on x if we are minimizing the L2 loss. Minimizing the L2 loss, this is what we want to do. Right? We want to find out this. But how to find out this? How to find out EY given x? There are a bunch of different ways. The simplest way is simply to average all the y values at this x. Right? Just average them. And that's a pretty good predictor for EY given x. Now the problem is we often don't have so much data, right? So if we do not have all the data, if we only see, for example, just one point here, then what I can do, I can slightly increase my window, and I can average all the y's in this window. Now, what happens when we have even less data than that, or when we have higher dimensions? It's the same thing. Okay? When we go to higher dimension or less data, we even don't have any data here. Well, in that case, we probably cannot do non-parametric. Non-parametric means we don't have any model. If we don't have enough data, that probably means we have to have a model, right? And the simplest model we can build is a linear model, one of the simplest. Right? The constant will probably be even simpler, but the linear model is one of the simplest model we can build. The linking, it only requires 2 data points for any linear model to do. But the linear model may not be the best model we want. Okay? Now, in this data set, we could do something like this, or we could do something like that, or maybe let's just link all the data points together and then give me an incredibly complex model. Which model is the best? Depends not on, right? We talk about the criteria for choosing the best model. The criteria is we should not try to find the best model that fits the existing data the best, right? The observed data best. We should try to find a model that fits the underlying population the best. And how do we know which model fits the underlying population the best? One of the trick that we can use is to split, what very commonly used trick is to split our data into training and a test. So that we can fit our model on the training data, right? Make them the observed data, and then we see how well it performs on the test data. The test data is basically a data set we never touch when we're fitting our model. So then after fitting our model, we take a look to see how well the model performs on the data it never seen before. And that's the true criteria for whether the model is a good model or not, right? To see whether the model actually fits the data that has never seen before, right? These are the data that we have never seen before. Whether a model can fit these data is the true criteria of whether the model is the best. So this is what we talked about in the first lab class. Now, in all this exercise, what we're doing is choosing the best model for this thing, okay? We're choosing the best model for this. This is what we call the target, okay? Target function is a target function. Because this is something that we want to learn or we want to estimate. Same, different words, same meaning. We want to estimate or we want to learn this target function, and then we can choose different models to best help us to learn this, to best help us to approximate the underlying target function. Right? The true target function, the true EY given x is never seen because it's in the underlying population. So we'll never be able to know that if we do not observe the underlying population. Based on the data we observe, we can try to estimate that. And how do we estimate that? We choose the best model to do that. Right? So that's what we covered in the first class. Now we sort of, after talking about that, we start to talk about causal inference, because causal inference is kind of a different beast. All right? Now for causal inference, our target function, okay, there we go. For causal inference, our target function is no longer this one. Okay? Okay, so let me just divide them. Let me just say the statistical problem is how to estimate this, okay? How to estimate our target function. That's a simple way to say that. One of the most common statistical tasks is how to estimate this target function. But for causal, what about causal? Well, for causal, we're not interested in EY given x. We're interested in something called EY, oftentimes given do x, okay? That's what we're interested in. So remember the do notation, right? When I want to know what is the x causal effect, what is the effect of X on Y? Okay? If my question is this, then what I'm interested in can be expressed using this notation, which says if I go and change X myself, what is the impact on Y? Right? And the differences between what we said doing versus seeing. For this one, UI given X, it is when I see some X value, I want to predict Y. Here is when I go and change the X value myself and see what is the effect on Y. And the reason why they're different is because if X truly has a causal effect on Y, then when I change it, it can change Y. If it doesn't have a causal effect on Y, then I change X, it should have no effect on Y. Right? So that's the do notation that we're talking about. Now, we finished last week with two simple sort of examples, right? The first example is hospitalization and health. We compared two different hospitals, hospital A and B. So we have hospital A, okay, and we have hospital B. Okay. Now, the causal and the statistical here may be different. For hospital A, people have 50% recovery rate. That we said last time. For hospital B, they have 90% recovery rate. And they could be, right? And so this is the statistical pattern that we see. But the causal pattern may be different. The causal question here is which hospital is the best, right? Which hospital is better for treating your health? Now, they're different because the people who go to A and the people who go to B could be fundamentally different. It could be that people who go to A are sicker. Right? They have a severe health issues. Maybe they have cancer. They have a very severe illness. So A may be a better hospital, but sicker people go there, and that's why you observe an overall 50% recovery rate. While B, on the other hand, may be actually a worse hospital, but people go there only when they have a little flu or something, right? So that explains the difference in the pattern. In other words, in this case, this is a case of statistical pattern that do not immediately reveal the causal relationship. Right? Statistical do not reveal causal. That's the sort of the lesson of this example. Now, I finished last week with another example which I ask you to think about. This example is advertising and sales. Now, suppose I am I'm a company, and I'm a marketing department. I want to know the sales versus my spending, okay, how much I spend on advertising. And suppose I have a data set. This data set contains all the historical spending and subsequent sales in the next quarter for a lot of different companies. And I see this positive relationship between spending and advertised spending and the sales. Right? I see this positive relationship. The question is this, well, surely this is statistical, right? This is a statistical pattern we can see. The question is about causal. Is there a causal here? Is my advertised spending causing the sales to go up like this? Right? And then, if you are in charge of the marketing department yourself and you want to decide how much money to spend this quarter, then you are really asking the causal question. You're not asking the statistical question. You don't care about other people or other companies historically, what they do and what their impact is. You care about if I spend this amount of money, how much sales do I get? And that's a causal question, right? Because you are doing it yourself. Okay? So the question is, could this causal relationship here be different than the statistical? Is it possible that this statistical relationship doesn't really tell us the causal? Is it possible? So that's the question that I leave you with last week, right? Any answers for this? Any reason why the causal may be different from statistical here? Anybody ever think about that over the weekend? Why the causal relationship may be different? Why if I spend this amount, the statistical says, if I spend this amount of money, I will get this amount of sales. Right? Is it possible that it's actually not correct causally? Any explanations? Great. Okay, that's a great answer. Right? Oftentimes, in many companies, right, when your sales go up, your profit goes up, and you earn more money this year or this quarter, so you have a large budget. You have a larger budget for advertising, right? So then, your marketing department gets more money, and then you can go out and spend more on advertising. In other words, it could be the sales driving the advertising, not the advertising driving the sales, right? Now, on the other hand, it could also be that maybe your previous quarter sales is really bad. Right? You had a really bad quarter, so you really want to sort of increase sales this quarter. That's why you increase your advertising level. It could also be that. So it could be good sales driving the advertising. It could be bad sales driving the advertising. But in whatever case, the sales could drive advertising, not advertising driving sales. And that's what creates the statistical relationship, right? So that's another example of statistical being different from the causal. So great, thank you very much. That's a great answer. Okay, so now these two examples just serve to illustrate the case where statistical do not agree with the causal. And sometimes we also say the correlation is not causation, right? Correlation is what you observe from the statistical relationship. Right? That tells the correlation between the two variables. And the causal relation is the causal effect of x and y. They could be very different. Okay, so we say the statistical problem is often to find out ui given x. The causal problem is often to find out ui given 2x. Right? So that's the causal of x on y. That's the statistical relation of x on y. Okay, so how do we find out this? Right? How do we find out ui given 2x? How do we find out causal relationships? In reality, well, there's a very easy thing to do. Okay, when you want to find out the simplest method to find this out, okay, to find out the causal effect of x on y, is to use a Nike slogan. Do people know what the slogan of Nike is? Just do it, right? Okay. So the Nike slogan, just do it. I have a video here.
Or anyone else to quit, and you're not going to stop there. Do it. Nothing is impossible. Do it. Make your dreams come true. Yes, you can. Yes, you can.
That's not a very good one. I'm sorry. But you know this famous video, right, by Shia LaBeouf on Just Do It, okay, as a motivation for, right, okay? The point is, if you want to see what the causal effect of x on y is, you can just do it, right? Just do it. And by just do it, how do you actually just do it? Well, you change the value of x, and you see what the y value is. That's that simple, okay? But oftentimes you're going to try many times. You're going to do it many times because the value of y can be random, right? Conditional onto x. The effect could be a little bit random. It's not fixed. Then you do x multiple times, right? So let me just say, suppose x is a 0, 1 variable. We call this binary variable. Now think about taking a drug versus not taking a drug. We want to see the causal effect of a drug on a person's health. Right? So x is a 0, 1 variable. Now how do you get this? Well, you get two group of people. In one group of people, you do it. You give them the drug, right? Let them take the drug. The other group of people, you do it. You make them not taking the drug, right? Force them to say no drug, right? So drug on one group of people, no drug on the other group of people, and then you compare the y, and that should tell you the causal effect of x and y. That's basically just do it. And what is that also called? That's also called what? That's called a random experiment, right? Okay. So what we just described is basically a randomized experiment. So the simplest method to find out the causal effect of x on y is doing a randomized experiment where you give x value to some people, you give a different value to some other people. In that way, you are just doing it, right? You're just doing the x, changing the values on different people, and to see how the y comes out. And that's the simplest method of doing causal inference. Okay? All right, so it's very simple. Now, so here's a picture of here. Okay, all right. So here's a picture of Ronald A. Fisher, the father of randomized experiments. He's also the father of statistics, modern statistics, together with Jerzy Neyman, right? And he's one of his best contribution, most famous contribution, is this book called The Design of Experiments, where he systematically developed the theory of causal, at least the early stage of using experiments to uncover causal relation between variables using the method of experimentation. The design experiments is a large field by itself, large subject. We're not going to touch that. I'm going to suffice to say that experimentation is one of the simplest way because you are just doing it. Okay, just do and change the x, see what the effect of y. Now, unfortunately, in reality, especially in economics, You probably heard many people say that economics is not experimental science to some degree, right? Because nowadays we have experimental science, economics, we have behavioral economics, and finance. But to a large degree, economics remains a non-experimental science. And the reason why is because experiments cannot be done on many topics that we're interested in economics. There's no way to do experiments, unfortunately. For cost duration, for dimensionality. Think about some experiments just impractical. So think about the question of monetary policy. Suppose a macro question, right? Suppose we're interested in the causal effect of a monetary policy. Say, I lower the interest rate by how much percent, or increase money supply by how much percent, right? If I do that, what is the causal effect on the economy? That's a causal question, and of extreme importance, of extreme interest to economists. Can we do randomized experiments? Can we say, okay, let's just take all these different countries in the world, and you lower interest rate by 1%, you increase interest rate by 1%, and let's compare the performance of the economy afterwards. Nobody will ever be able to do that, right? So no randomized experiment can be done on most topics in economics. That's why we cannot rely on experimentation a lot. There's another reason that explains why experimentation in economics is rather limited so far, which is people are so different. Okay, now even if so I just give you a macro example, but even if we're talking about micro example, suppose I want to know if I give you this amount of money, okay, how would you like to? What is the impact on your life? Okay, so suppose you're from a poor region. We want to know that if I go to extremely poverty region, if I give people like 1,000 loan, and I want to know what is the effect on that person. Will that person start using that loan money to invest, or will that person use it to gamble and use some other useless activities, or will that person do some other things? Right? I want to see the causal effect on that. Now, for that, I could do experiments, and indeed that's what people do. Right? People do field experiments, lab experiments, where people do give people these different treatments and observe the outcome. The problem is, oftentimes the results of these experiments do not universally apply. Why? Because people are so different. So I could do experiment on all of you. I can give you some of you this treatment. I give some of you that treatment, and I can observe the outcome, and I can write a paper out of it. The problem is you are is a very specific group, right? You're young, you're college kids, you're in China, right? And the result I get from you probably do not apply to any other group in other region. Right? So if I'm interested in what is the effect of giving a loan to poverty-stricken areas in sub-Saharan Africa, and I do experiment on you guys, the result probably do not apply. Right? Now, on the other hand, if you think about physics, okay, or chemistry or natural science, anywhere in the world you can do some experiments on molecules and atoms, and your result hold universally, right? That's the same thing. But anywhere in the world in economics, if you do experiments on people, because people are so different, our culture, institution, language, everything is different, the results probably is very extremely what we call local, that do not apply universally. And that's a great limitation. That's a huge limitation on the usefulness of experimentation in economics. Okay. So unfortunately, in economics, we oftentimes have to rely on observational data rather than the experimental data. We cannot do experiments. We have to rely on what we observe, what we see. But what we observe or what we see do not tell us causation directly. It tells us correlation directly. Right? So for all the data we observe, okay? So these are the data we observe. It's not from experiments. For the data that we observe, they tell us correlation. They tell us this thing. Okay? This is what we can get from the data we observe. However, we want this. Okay? We want this. So we want this, but we're not able to do it directly because we're not able to do experiments. Okay? So this is what we have from data. We can try to estimate this from data. This is what we truly want. So the problem causal inference is very simple. The problem of causal inference is how to express this thing in terms of this thing. Okay? This is something I can get from data. This is something I want. If I can express this thing, this object, in terms of this object, then I'm done. Then I can get causal relationship from the data. Okay? So let me tell you. So let's go through some very, very simple examples of how to do that. We spend essentially the second half of the semester doing this. All right. But right now in the introduction, let me just walk you over a very, very simple example of how to do that and what I mean. Okay. All right. So it turns out that, let's say I have three variables A, B, C. Okay. Suppose I have three variables A, B, C. Now it turns out that in order to do causal inference, I need not only data. Data is not enough. I need more than data. I need some knowledge about the underlying relation, the underlying mechanism that generates the data. You have to begin with a mechanism. You have to begin with some knowledge about the underlying causal mechanism that generates the data. And then you can do causal inference. If you only rely on data, then you can only get statistical relationship. So the way to go from statistical to causal is to first think about the underlying mechanism. Once you have them, you can find a strategy of turning statistical into causal. So let me illustrate. Okay, suppose we have three variables A, B, C. Now the underlying causal relationship between A, B, C, there are many different ways that these three variables can be linked. So one way is C could cause A, C could cause B. Okay, so that's one kind of relationship that you believe that could generate the statistical data we see. Okay. So this is called, in this case, C is called the common cause because it causes A and it causes B. So it's a common cause. Now there's another type of relationship between these three. A could cause C and B also could cause C. In this case, we say C is a common effect. It's the effect of A and the effect of B. Right? Now, of course, we can also do that. We can have A cause C and we have C cause A. Okay, C cause A. And in that case, we say C is a mediator. It stands in the between. Right? Now, regarding, see that I have not put any arrows between A and B, because here's something I'm not sure. I do not know whether A has a causal effect on B. So that's something I want to find out. Okay? So I want to, using my statistical analysis, I want to find out if A has a causal effect on B or not. But right now, I'm not sure. The things that I am sure, I know, is that A cause C, C cause B, or C cause A, C cause B, right? So that's the thing I know. Let's start with that, okay? Let's start with that, and let's see how we can proceed, okay? All right, so let's see, suppose I have A, so suppose I have C, okay? And C causes, let's begin with this situation. C causes A, and C causes B. Suppose. Let's start with that. That's my assumption. Okay, that's not something I get from data. That's my assumption about the causal relationship. Now, my first question is this: suppose this is the case, is A and B correlated, or are they independent? Now, I'm assuming for now. Let's assume that A and B has no causal effect on each other. A do not cause B, B do not cause A. So that's everything. Okay, that's everything. If that's the case, is A and B correlated, or are they independent?
Correlated.
They're correlated. Why? Can you give me an example? That's the correct answer, by the way. Okay. Can somebody give me an example of correlation in this case? Please.
下这个时候来冰不能拿溺水，我就不能说因为
溺水。
溺水就是
Oh, okay, okay. Yeah.
我就不能说因为卖冰我们导致了，不能说因为卖冰我们
Okay. All right. So thank you. So the answer is, let C be summer. Okay. Let C be summer. Now summer will cause you to buy ice cream, right? Will cause you because it's hot. And I'm going to modify your answer a bit. Summer can also cause you to swim, right? Swim a lot, swim more. Okay. Swim more. Okay. Swim more. Now, are these two? If suppose we have two kinds of data, right? One data is ice cream consumption by quarter, by time of year. The other is swim frequency by time of year. Are these two correlated? Of course they're correlated, right? Because suppose you have two time series. One time series is over the year. What is ice cream consumption, right? Ice cream consumption, and the other is over the year how much do people swim, of course they should be correlated because when they are high, it should be summer, right? Summertime. Okay? In the summer, people swim more and people consume ice cream more. So the two time series has to be correlated. But there's no causal effect. Buying ice cream obviously do not cause you to swim. Well, at least I believe, right? Swim does not. Maybe swimming afterwards, after swimming, you want to consume some ice cream, but I don't know, right? Let's just say they have no causal relationship. They are correlated. Okay? The example I gave you in my slides is C is smoking. Now, smoking unfortunately may cause you to have a higher probability of developing lung cancer, right? Unfortunately, okay. So there's a causal relationship in that. The smoking may also cause you to always bring a lighter with you, right? You always bring a lighter, obviously. Okay, that's a smoke. Now, obviously, these two things are, and now the question is, are they correlated? So if you observe two group of people, one group of people always carry a lighter with them, you don't know anything about these people other than the fact that these people also always carry lighters. The other people never carry lighters. Now, if I want to ask you to predict which group has a higher probability of lung cancer, obviously you predict the group of people who always carry lighter with them, right? So they're correlated, but obviously they have no causal relationship. I could carry a lighter myself because I wouldn't want to play with matches. Does it give me higher lung cancer probability, right? So these two variables are correlated, but they have no causation. Okay. So now let me ask you, if I'm interested, suppose I say that right now I assume they have no causal relationship, right? But suppose I say there may be, it could be, A could have some causal relationship on Y, on B. It could, but I'm not sure. I want to find it out. Can I find it out by looking at the correlation between A and B? Can I find out the causal relation between? So let's now assume that A could have relationship on B, causal effect. It's just that I'm not sure, right? Can I find out the causal effect by looking at the correlation? No. The answer is no. Why? Because even without causal effect, they are correlated. Okay? So in other words, the correlation contains non-causal things. So I cannot simply looking at the correlation and deduce the causal effect from that. In other words, in this case, E, B, given A, okay? The expectation of B given A, which is statistical. This is a purely statistical object. In this case, is not equal to EB given do A. Given to A. Right? So the statistical correlation is not equal to causation here. Right? And the reasoning again is because even without causal, they are correlated. Okay. Now let's take a look at another relation, which is A cos C and a B cos C. And again, I'm going to assume that there's nothing between A and B, no causal effect. Assume, okay? Now in that case, is A and B correlated or are they independent? Think about that. They're independent. Okay? They're independent. Again, you can think about a million examples of why this why this is the case. Okay? So when I'm hungry, let's say it's hungry. When I'm hungry, I wanna eat, right? When else do I wanna eat? So when I'm hungry, I wanna eat. This may be hungry. Let's say lunchtime. Okay. So when I'm lunchtime, I wanna eat, or maybe after exercise, when I exercised, I wanna eat. Okay. So they all both lead to the same thing. But obviously, lunchtime exercise has no direct causal relationship, right? So that you have a million examples you can do. So they are independent. Okay. So A and B are independent. Now let me say, suppose A could have causal effect on B. Could. Okay. A could have a causal effect on B, but I'm not sure. In that case, can I find out this causal relationship by observing the statistical correlation between A and B? Can I or can I not? In that case, if I look at the correlation between A and B, does the correlation tell me about their causation? That's the question. Yes or no? Again, this is my picture. A goes to C, A calls C, B calls C, and I actually see some correlation between A and B. Does that correlation tell me causation? Thank you. The answer is yes. In this case, correlation tells you about causation. Why? Because without causation, there is no correlation. Okay? In this case, without causation, no correlation. That's why if we ever see any correlation, it has to be because of causation. It's that simple. So in this case, we can write EB given A is equal EB given to A. Okay? We can write that because in this case, the correlation tells us about the causation. Now, as you can see, it's the idea is we want to find out the do, right? We want to find out the causal. But the only way we can get the causal is that we somehow try to find some statistical relationship that we can get from data that corresponds to this causal thing. If we cannot find any statistical relationship that will tell us the causal, then we are doomed, in a sense. That's the whole practice, that's the whole enterprise of doing causal inference. So in this case, it's very simple. This EB given to A is simply equal to EB given A, because the correlation equal to the causal. Okay. Now let's go back and let's again talk about the case of C going to A and then C go to B, okay? We're back to the first case, except that, so we know from this case that A and B are correlated, even if there's no causal. When there's no causal, A and B are still correlated. Now what I'm going to do is I'm going to condition on C. And by the way, when I write this, I mean condition, okay? Condition on C. Do people know what condition on C means? Control, exactly. Yes. Okay, so when you condition on something, you have all learned the conditional probability, but intuitively, when you condition on something, it means that you're controlling or you're fixing that. You do not allow that variable to change, right? That means conditional on, intuitively. So let's suppose C is smoking, again, right? Now smoking is suppose it is a 0-1 variable. It may not be, but suppose it's a 0-1 variable. By controlling on C, or by conditioning on C, it means that I fix smoking. It means I only look at people who smoke, or I only look at people who do not smoke. Okay? Now suppose let's condition on C equal to 1, means I only look at people who, actually condition on C equal to 0, okay? Let's do that. Let's condition on C equal to 0 means I only look at people who do not smoke. Remember what A is in our previous example. A is a lighter, right? He's carrying a lighter with him all the time. B is lung cancer. Now we just said that these two variables are correlated. If you observe the people always carrying a lighter, and you could predict that person has a higher probability of lung cancer. Now I'm conditioning on C equal to 0, meaning I'm only looking at people who do not smoke. In that case, carrying a lighter and a lung cancer, are they still correlated? They're no longer correlated, right? They become independent. Okay? Carrying a lighter no longer helps you predict lung cancer because you know that person doesn't smoke. So the story here is very simple. Once I condition on C, A and B become independent. Now let me say this, right? Now let me say that I suspect that A could have some causal on B, could have some causal effect. I'm not sure again. I want to find it out. In this case, can I find out the causal effect of A on B by looking at the correlation between A and B, but conditioning on C? Yes. Okay, very good. So in this case, again, the correlation becomes the causation. Okay, correlation tells us the causation again after I conditioning on C. So I could write E A given B given to A. Right? So I want to know the causal effect of A on B. So E B given to A, but also conditioning on C. Okay, also condition on C is equal to EB given AC. Okay? So this is purely statistical game. The expectation of B given AC, right? So B given A, but also given C. Given C means conditioning on C, right? So this is the statistical relationship between A and B, but conditioning on C as well. And this is purely statistical, which I can estimate from data. Now this is a causal thing, right? So this is a causal because I'm interested in, after condition on C, I'm interested in the causal effect of A on B. So this is a causal object, and this is statistical. And in this case, we say, once I condition on C, again, the statistical tell me the causal. And I'm able to estimate this causal effect from data again. So as a reminder, as a recap of what we're doing here, I have two things, EY given X, or maybe some other variables, right? Okay, X doesn't have to be one-dimensional. I have two things. So this is a statistical object. It's essentially, you can think about it as coming from the correlation between X and Y. This is what I can get from data. I can estimate this from data. Now this is what I want in a causal inference problem. This is what I want. In order to get this, I need to find a way to express this in terms of this, because I can estimate this from data. And here I do it, right? How do I do it here? Condition on C. Once I condition on C, I have successfully expressed something causal in terms of something statistical, and I can estimate the statistical thing from data. And boom, my task is complete. Okay? From statistical to causal. Okay? All right, so let me ask you. So this is a very simple example, right? Obviously, in reality, causal inference is a much more complicated task, but this is a pretty good illustration of how causal inference works. And it shows us the big principle, the big sort of the underlying idea about causal inference. So let me ask you about the connection between the statistical learning or statistical modeling and the causal inference. Okay. So after this little example, remember what I said about this, the plan of this course. The first half of this course, we're going to strictly focus on statistical. So we're going to talk about statistical modeling and choosing the best model. So I said, okay, there's this model, right? This model. We're going to choose the best model. And I'm going to introduce to you a lot of different models. So we're going to talk about linear model, right, which you have already learned in your econometrics class. Polynomial model, which you have also already learned. But we're also going to talk about some more sort of advanced or state-of-the-art models, nonlinear models. We're going to talk about nonparametrics. We're going to talk about some machine learning models, like like trees and random forest, like SVM, support vector machines, support vector regression. We're also going to talk about neural network briefly. Right? So we're going to talk about all these machine learning models and the latest models that people use in the statistical community. And then we're going to talk about causal inference. So the question is, now that I have walked you over this very simple example, the question is, what do you think is the connection between causal inference and the statistical or machine learning? What is the relation between them? Remember, machine learning or statistical modeling is about finding the best model to describe some data, right? So you can also think about the task of machine learning is find out the best model to describe this thing, okay? Because we do not know this, right? This is the underlying population. So we need to find a model to estimate this thing, right? To EY given X. So finding the best model is a task of statistical modeling or machine learning, right? Same thing, okay? Just finding the best model. Neural network, support vector machines, random forest. These are just different models that they look differently, but they can all be used to estimate this object, right? So that's the first half of this course. My question is, what is the connection between what we're doing statistically and what we're doing here causally? Right? How do we use what we learn from machine learning to causal inference? That's a very simple question. Okay? After this little example. Do people have anybody venture any answers? So after I give you this example, think about the connection between the two. Or let my question be more specific. Suppose you have learned a neural network from my course. Okay? Many of you have already learned that maybe, but suppose you have learned neural network from this course. How do you use neural network to causal inference? How do you do that? right? So the answer is, I will just say that, I will just proceed, okay? So the answer is actually very simple. Causal inference, two-step. The first step is, how do I get something from causal to statistical? Okay, so I want to express my causal object in terms of something I can estimate from data. Given this example, I know that if I control on C, once I condition on C, the causal becomes statistical. But this is only the first step. The second step is to estimate this from data. We still do not know this thing, right? Now this thing could be estimated from data because it's a statistical object. When I estimate from data, how do I estimate? I need to pick a model. Okay? And I could pick any model I want. I can pick a linear model, I can pick a polynomial model, I can pick a neural network model. So it is in this step, this is step 2, that we can apply any machine learning and modern statistical methods to step 2. Step 1, this is step 1. Step 1 is how to express what is our intended causal relationship in terms of a statistical relationship that we can estimate. So the first step is purely causal reasoning, okay? Causal reasoning, and the second step is applying statistical methods, okay? Applying statistical methods, which includes machine learning models and all the other models that we can think about. Okay? All right. So that's really the connection. Now, let's go through another example which you're all familiar with. Many times in your intro econometrics class, the relationship between wage and education, right? Okay, schooling. Let's call it schooling. Schooling, right? How many years of education you have had, and what is your wage level, right? How much income you have. That is the archetypical question that everybody learns when you're doing econometrics. And you all know that if I do a regression of wage on schooling, that doesn't necessarily tell you the causal relationship, right? Okay, that's a correlation, not a causal thing. So now let me ask you, why is it not causal? So let's say wage is one variable. Wage is one variable. Schooling, right? Schooling is another. Okay. What is the underlying mechanism? So why is wage and schooling? Why the correlation doesn't tell me causation? Can you explain this using something like this? Now, in this case, we say A and B, the correlation doesn't tell me causation because there's some C that causes both A and B. If there's a C that's a common cause, then A and B will be correlated even if there's no causation. That's why correlation doesn't tell us causation, right? What about here? Yeah, very good. Okay, so I see already people answering. There's some C here that is essentially ability, right? So ability will give you a high, if you're a capable person, it'll give you a high wage. If you're a capable person, you obtain more schooling because you can. If you're smart. If you're smart, you get more wages, smart, you get more schooling. And that's the C, right? That's the C variable that we have here. That's why wage and schooling, even if there's no causal, even if schooling has no causal effect on wage, they're still correlated because of this C, right? This ability. Okay, so E schooling given wage, E wage given schooling, which is the correlation between wage and schooling, is not equal to E wage given do S, which means the causal effect of S on wage. So how do I turn the causal into statistical? How do I do that? We control for ability, right? I think that's what you always learn in econometrics. Right? You need to control for ability. You need to condition on ability. Okay. Now let's, of course, as you all learn in econometrics, that ability is something that you do not observe. But suppose, for simplicity, let's just assume that you observe ability. For example, suppose that in my data I have your test scores. Let me just suppose that test score is a pretty good proxy for ability. So we observe ability. Okay, suppose, because we have data on test scores. Just imagine that. All right. So once I have data on ability, like test scores, I know that when I control on it, when I condition on it, then if I do that, then the correlation between the two tells me about the causation. So, in other words, E wage given do schooling, causal, but conditional on ability is equal to, okay, all right. So it's equal to what? This thing, okay, is equal to E wage given S and A, because that is a statistical relationship between the two. They're equal once I condition on ability. But this is only the first step. Right? This is the first step of our causal inference, which is purely causal reasoning. There's no statistical thing we're doing here. Okay, it's pure causal reasoning. But only reaching this step is not enough. Here's the second step. The second step is, now I have data, I have a bunch of data on W, Wi, Si, right, and Ai, right? So these are my data. How do I estimate this from the data? That's the second step. And the second step is purely statistical. Okay? So how do I estimate this from data? Well, I can use a model. What is the model that you use in your econometrics class? A linear model. The model you use is W equal to beta 0 plus beta 1S plus beta 2A plus E, right? That's the model you use, right? But that's a linear model. It's basically, suppose these are SA, okay? I'm just going to combine SA into the single dimension. Suppose these are SA and these are W, and these are your data, right? What you're doing is you're estimating this object using a linear line, okay? Using a linear line. That's what I'm doing. But that's not the only statistical model you can use, guys, okay? It's far from the only one. We have numerous models we can use to estimate this. Any models we're going to introduce in this class, like a neural network, like a random forest, right? Like a support vector machines, or maybe just simple vanilla linear network, linear model. All these models can be used at this step to estimate this object. Okay, to estimate this object. You don't have to use linear. You can use a really nonlinear thing. And the goal at this stage is actually choosing the best model. Choosing the best model to basically estimate this object. And how do you choose the best model? Well, training, test, right? You look at the population area. That's what we talk about in the first half of the class. Traditional econometrics focus on the first step, which is what are the variables we need to control in order to get the causal relation we want. That's what the traditional econometrics is mainly concerned about. Traditional econometrics don't care about the second step. In the second step, people typically just use a linear model. Okay? But you can, as this course hopes to show you, that in the second step, we can use far more than a linear model. We can choose the best model to fit these data. Okay? And in doing so, we can make our causal inference much, much more accurate than the current way of doing things. So that's really the overall plan for the majority of this course. Okay? All right. Okay, so that's all I want to talk about for the beginning of causal inference. Now the third part. So the course is really two-part, statistical learning and causal inference. But the causal inference part, actually, there are another two parts to the causal inference. I'm going to talk about the second part of the causal inference now. Maybe you can think about it as the third part of this course, which is structural estimation. But before doing that, let me go to okay. All right. Now, for those of you who are grad students here, you may have heard the term reduced form and structural estimation. Or you may not, right? If you may not, that's perfectly okay. But one of the things that even when I was talking about causal inference, I said, look, the first step, turning this into this, right? Turning what is causal into a statistical object that we can estimate data using data. The second step is finding the best statistical model or machine learning model to describe this object, right? To fit the target function that we want. That's a two-step procedure. But that procedure is also what we call reduced form in economics. Traditionally, this approach has been called reduced form econometrics. It turns out that is not the only way we can do things. There's another way called structural econometrics. And these two schools have been fighting with each other for a long, long, long time. In this course, I'm going to introduce both to you, and I'm going to tell you how I think they should be united, right? Okay. But one thing, starting from here, right? One thing you can see from this whole procedure is that there's almost no economic model here. There's almost no economic model or economic theory. Do you see any theory here? Well, there is some theory, right? This is kind of a theory, right? This is a theory. But this is not a mathematical model. This is not an economic model, that is, right? So we do some causal reasoning, and then we find a statistical model to describe it. And when you do that, you have not really used any economic model that economists have developed, correct? So this is a problem facing a lot of economic student, which is you have learned microeconomics, macroeconomics, finance, and all these different courses, pure theory courses. And you have used a lot of different models. Right? You learned a lot of different models in all these different courses. And then you go to econometrics, which is analyzing data, and you see no relation to macro finance. You see no relation. Because in econometrics, all you do is running regression. Correct? So econometrics is just data analysis. And it seems awfully just like statistics. So what is the use of this economic model if you never use them? Okay. Well, the answer is that's because you are doing reduced form econometrics. So econometrics, there are two schools, reduced form and structural. And for structural econometrics, these people take economic models very seriously. They start with economic model. They start with your textbook macro model and any other models developed by theorists in recent years, and they apply those models to the data. They fit those models to the data and see how well the data describe the model. And then they use the fitted model to make predictions and do policy analysis. That's called structural econometrics. So the structural people really use your economic theory rather than simply relying on statistical models to do that. Okay, so give you an example. Let's see an example, right? Actually, somebody asked me this question last week after our second class. There's the relation between, I'm again going to use the relation between wage and schooling, right? Okay, wage schooling. So there's some relationship between wage and schooling. And we can estimate it using something like this, right? Now the problem is, what does economic theory say about this? In economic theory, how does schooling and the wage, what's the relation between them? Do people know? In your Econ 101, right? In your principle of economics class, how do you determine wage? How is wage determined? Do people remember? Let's think about the simplest model you can think about. What is that? Yeah. Okay. Already, I think I already hear a very good answer. The simplest model that explains wage in labor market is there's a supply, right? There's a labor supply. There's a labor demand, right? And the equilibrium is your wage. That's the economic theory, right? Okay. Now, let's suppose schooling is a 0-1 variable. So suppose 1 means you have a college degree, 0 means you have no college degree. Then I'm going to say that let this wage be the wage of college versus the wage of no college. Okay? It's called wage premium for college students. Then you can write this as the supply of college students, right? This college versus no college. You can write this as the wage of college versus wage of no college, right? And this is the demand curve. Sorry, not this. This is demand, okay? Demand for college versus demand for non-college. like how many high-tech jobs there are in the world, right? In this economy, and this is how much educated people are. And the equilibrium is the wage premium that we have. In other words, when you go to college, so when we do this, when you do this regression, you are assuming that your schooling level has a fixed causal effect on wage. But in reality, the causal effect of your schooling, of your education level on wage is equilibrium, right? It depends on what? It not only depends on you, it depends on how many people in this country are college educated. It depends on what kind of jobs this country has offered. Okay, if this country has a lot of high-tech jobs, has a dynamic economy, then the demand curve is high, it demands a lot of college labor. Or if the country gets, produces a lot of college labor, but the demand is low, then whether here or here. Okay? So it depends on the underlying factors, right, according to our economic theory. So when you do this reduced form, you're not taking into consideration all these things at all. Okay? You just assume there's some kind of fixed effect out there. But when you respect economic theory, when you take economic theory seriously, then this is how the wage should really be determined. So what do structural economists do? Structural economists take this very seriously. So they estimate the demand function, supply, right? They estimate the supply function, and then they estimate the demand function, and then they produce the equilibrium wage that fits to the data. Okay? So in other words, they try to fit that data, they try to fit that model such that the model will produce the wage that we observe. And the model will fit the demand curve and will fit the supply curve. And once you do that, you basically have the entire labor market model out there, right? And then you can use this model, this estimated model, to do any kind of prediction. For example, you can predict what happens when, let's say, 高校扩招, right? So when in China, suppose we produce much more college students than before, you can use this model to predict what happens. Basically, the supply, you have done this in principal economics many of times, right? So the supply curve goes down, we have a lower wage equilibrium, etc., etc. So you can use the model to do all these kind of predictions if you do structural econometrics, which you cannot do if you do the reduced form approach. So this is the difference between reduced form and structural. Now, in this course, we do not have time to really go over structural, show examples of structural papers, but I will talk about structural modeling, the principles, and when you use that. And then based on the learning in this course, you can go ahead yourself and learn about structural approach. Where we're spending majority of the time on the reduced form approach in this course, but then you can go ahead and read structural papers by yourself. But I will give you a unified theory about how they relate and when you use this and when you use that. But before continuing on structural estimation of structural econometrics, let me just say, here it is, I always forget. Econometrics as a word, right? So when we have econometrics as a word, econometrics, the word began, actually is coined by Ragnar Frisch, who is one of the founding fathers of the American Econometric Society. And this is what he said in 1923 when he became the first editor of Econometrica. Okay, he said econometrics has its aim to subject abstract laws of theoretical political economy. Economics at that time was called political economy. To subject the abstract laws of theoretical economics to experimental and numerical verification. So the idea is, why do we need econometrics as a separate discipline? Is because we want to apply economic theory to data. That's what he said, right? In short. And he later wrote, so far, we have been aware that we are unable to find any better word than econometrics. So we are aware that in the beginning, somebody might misinterpret the word to mean economic statistics. No, that's not economic statistics. Because we believe we'll soon be clear that everybody clear that we're interested in economic theory as much as anything else. So in other words, econometrics, the subject, when it was founded, the specific goal is to fit in the theory to data. Okay, is to apply the economic theory to data. Now later on, as throughout history, when it's being developed, the discipline becomes the theory becomes less and less used in a way, right? And then we have two schools, structural and reduced form. In the reduced form approach, the economic theory was almost never used. other than being used as sort of a causal reasoning step when you just reason what might be needed to control, but you don't specifically fit that model to the data, right? But that may not be the founding intention. What I'm saying is, since its beginning, econometrics should be, or at least in the beginning, it is conceived as a discipline that fits economic theory to data, not just running theoryless regressions. Okay, so that's just a historical note on that. Now, let's come back to our slides introduction. So in today, what I'm going to do is I'm going to give you two examples of structural model in structural econometrics in practice. Okay, in action. The goal of this is not to tell you how to do it. The goal is to show you the power and when it could be used, structural econometrics, why it's good. So the first example, this is a pure example. You don't have to understand how it's done. It's pure sort of like a presentation of structural econometrics. The first example is auction. Now, for those of you who have taken game theory class, you have learned auction models, right? Okay. Has anybody not taken game theory class? Well, now I hope you remember your auction model. So this is data from auction, repeated auctions, the first price auction, right? The x variable here is the number of bidders, how many bidders participate in the auction, and this is the winning bid. Okay? Why is the winning bid? Now suppose we're doing first price auction repeatedly on the same type of object, and you see this positive correlation between number of bidders and the winning bid. Okay. All right. So So what is our goal? Our goal is I want to predict winning bid. So X is the number of bidders. Y is winning bid. So my goal is I want to predict Y using X. The first approach is reduced form. And the reduced form approach here is extremely simple. Basically, EY, winning bid given X, here it's basically just EY given to X. Just given Y to X. Now, why is that? Okay, so when we reach this conclusion, we need to use some economic theory. Okay? Because this step, causal reasoning, is actually based on, it is indeed based on our understanding of the mechanism. It's just that we don't have to specify a mathematical model for that. So in according to economic theory, according to our understanding about auction, how is winning bid determined? Well, winning bid is determined by everybody trying to what? So people who participate in the auction, right? They try to find the best way. They basically give an optimal bid. They bid what they think is the optimal depending on their strategy. And the strategy is to maximize my ability to get the thing I want at the price I can afford, right? So everybody does that, and whatever comes out the highest is the winning bid. So in other words, the number of participants in an auction and a winning bid should have and suppose everybody who participates in this auction has essentially they all come from the same distribution of their underlying values. If you don't understand, that's okay. But all I'm saying here is there's nothing in between them. Okay, so X has a direct causal effect on Y. There's no C. There's no something that causes X and causes Y. Okay? Just people who randomly participate in this option. So there's a direct causal relation between X and Y. So basically, I can write this. Now remember, in reduced form, we have two steps. The first step is writing the causal in terms of statistical. The second step is very easy. The second step is simply finding the best statistical model for EY given X. So how do I do that? I can fit a linear model. Okay. Right. So actually, okay. So I can fit a linear model. This is a linear model. I can use it to describe the relationship between X and Y. I can fit a quadratic model, which is the green one. Okay. That's also described. That can also be used to describe EY given X. Or what? Or I can treat economic theory in a very serious way. I can fit the economic theory, the mathematical model, to the data, and use the model to generate my prediction. And that's the structural approach, which is this red one, which I call a model. Okay, model. So what is the model? If we really want to use economic model, what is that? Well, I'm not going to go over all the derivations, but if you remember from your auction class, right, Suppose I have n people, x people, right, participate in the auction. Then what is everybody's strategy? Suppose everybody has a value, this underlying value, of how much the object is worth, and the B is my bid, V is how much I value the object. Then if I ever get it, if I win the bid, if I win the auction, then I get V, but I have to pay my B, right? Because it's first price. Okay? And then times the probability that my B, okay, my bid, is larger than all the other people's bid, right? Correct? And then we have a maximize. So now I need to choose the bid that maximizes my return, right? This is my expected return. This is assuming that there are a lot of assumptions here. One assumption is I am risk neutral, so because this is a risk neutral calculation. The other assumption is that everybody has the same IAD value that we have for the object. Now, if we believe in this model, then I have this very simple conclusion, which is my bid. Okay, so you can use mathematics, right? Derive the consequence. So the BI turns out, if you believe in this model, then BI, it turns out, is VI minus 1 over n minus 1. N is the number of bidders in the auction. GB, the large GB divided by the small GB. The large G is the CDF function. The small g is the PDF function. Okay, all right, so that's CDF divided by PDF. We have this mathematical formula. And this B is the distribution of B. So this is the CDF distribution of the observed bids. This is the PDF distribution of the observed bids. Now, if you look at this formula, what immediately tells you is what? Is that if you truly believe in this theory, then when you observe people's bids, you can deduce their private value. Okay? Now, the private value V is never observed, right? You never know that. You only see people's bids. But this formula tells me that, look, the relation between B and V is very simple. V is simply equal to B plus the observed bids plus this thing. And this thing I can always estimate from data because it's the PDF and the CDF of the observed bids. So in other words, if you have to trust my derivation here, right? But in other words, when we believe in this theory that from the observed bids, I can basically guess people's underlying value. And that is very, very powerful, okay? Think about that. You watch people's bids, and I see your bids, and I immediately know how much you actually value the object in your heart, right? That is actually what this formula tells me. And I can estimate everything. So using this strategy, using this formula, I can go to each auction, and I can estimate people's underlying value. And then once I estimate people's underlying value, then I can make predictions, right? Okay? Then I can make prediction. The prediction is here, right? So given this amount of bidders, what is going to be the winning bid? I can make this prediction because I have already estimated people's underlying value. Of course, the highest value one who give the highest bid, and the highest bid is my prediction. And why do we have this relationship? Like, why is it increasing but with diminishing marginally it sort of increases slower and slower? Why is that? Why is it concave? The reason is because the winning value, right, the highest value, if you draw a number of people from the same value distribution, the more you draw, the more likely the highest value is going to be increased. But it's going to be increased slower and slower and slower, right? So if I draw one value from a distribution versus I draw 100 value from a distribution, the 100 value likely, the maximum of the 100 value likely to be much higher than the one value. But however, if you go from 100 to 200 to 300, the increase may be slower and slower because it's harder and harder to get a higher and higher max V. Okay, so that's the intuition behind why this relationship is this concave and increasing relationship. Okay, so now I've introduced three types of models. Two are statistical or reduced form. The other is structural, right? So this red one is structural, is model. We have a linear, we have a quadratic relationship. Which one is the best? The question is which one is the best? Now, from this graph, it seems that even if the red one, the model is correct, it seems that the red model, the structural estimation, prediction, is very close to the quadratic relationship. Right? So it looks like I could just go with quadratic, because quadratic is so much easier. It's a polynomial equation. It's very easy to estimate. So it looks like the quadratic is much easier to estimate. The structural estimation takes a long time. It's complicated. Right? We have to do the model. We have to use the equation. We have to do all these different things. So the structural looks, there's no need to do structural. I can just do quadratic. Is it true? Well, in this range, it's true, because that's all our data. But if I want to predict something that's far away from my existing data, suppose I want to predict what happens if we have 50 bidders. Now, right now, we only have until 25 bidders, right? The maximum is 25 bidders. If I want to predict what happens if we have 50 bidders, what is the winning bid? Then you see a huge difference between the three models. Okay? The linear model go all the way up, the quadratic model go all the way down, and the structural model give you something like this, right? And obviously, in this case, the structural model is much more reasonable than the other two, correct? If we go to x equal to 50. Okay? So, two things about this, right? The first thing is, if you're only concerned, right, if we compare structural versus non-structural, if your only concern is making prediction within the range of your data, then you probably don't need to do structural. If you fit a good reduced form statistical model, it's probably going to be pretty good prediction. But once you go outside your observed range, and in statistical terms, it's called extrapolation or generalization. Okay, if you want to go outside your existing range of data, if you want to go outside, then you need a model to give you a good prediction. Okay, the statistical model probably don't work in that case. Don't work very well. Why? Because we never see these data. These are the data we see. So we can always find a statistical model that fits these data well. But for unseen data, and especially for unseen data that's out of the range of the observed data, then if you don't understand why it behaves like this, you will get a very bad prediction. Remember, using economic model or using structural model, economic theory, is about using what you understand about the underlying mechanism in order to generate your prediction. Okay? When we're fitting our model to data, we're using what we understand about the underlying mechanism in a very serious way, in the sense that we are using the mathematical formula to do that. Okay? Now, the broader idea, the broader point here is whenever you want to extrapolate, whenever you want to go outside your existing range, you need a better understanding. You really need understanding about what's going on here in order to generate a reasonable prediction. If you don't base your prediction on understanding, then your prediction may be very bad. Now, give you an example in in economics and finance, right? In finance, you all know that the financial crisis, right? The recent the 08 Great Recession, global financial crisis, was caused by subprime loans on Wall Street, right? And one of the problems with subprime loans is that when people try to estimate, because people have mathematical models for the CMOs they build, right? For collateralized loans they build. And when they build collateralized loans, what they do is you know how it works, right? You pool different mortgages from all over the country into a pool, and you divide it into different tranches. But when you issue those kind of products, the analyst's job, the quant's job, is to predict the default probability of each tranche, all right, of each product. So how do you predict default probability? Well, you use historical data. Okay, so it's a prediction job, right? You want to predict default probability for mortgages in a pool. Now, what they do is they look at historical data, but unfortunately, at that time, historical data only went back as far as in the 90s, right? Maybe a little bit 80s, but 80s and 90s mainly. Now, the problem with the U.S. housing market is the housing price was increasing, had been increasing from the 1990s all the way until 2005, never decreased for once. Okay? The housing price was always climbing. So in your historical data, housing prices always go up. And when you fit a model, when you fit a statistical model to that data, you are within this range of housing price always go up. So so in that sense, you can never accurately predict what happens when the housing price starts to go down. Okay? Right, so your mortgage default rate data is based on an environment in which housing prices always go up. Suppose I want to estimate the default risk when the housing market go down. How do I estimate that? Well, I have to understand people's default behavior. I have to have a serious economic model that describes when people will default. Okay, you have to have an economic model, a theory about default behavior, and you really want to understand the underlying mechanism in order to make a truly good prediction of what happens when the housing market goes down. Otherwise, if you just simply fit a time series model, you can never go outside your existing range. Right? So that's a limitation of traditional time series approach. When you try to predict stock market returns, when you try to predict default rates in all these cases, is because traditional time series approach is only statistical. So it can only apply within this range. Okay? Once you try to go out of it, you can use a time series model to predict maybe in the next month or next week's stock price, but you can never do that for 10 years after today, right? Because why? Because in order to do really far away from your existing range, you really need to understand the underlying mechanism. You need to have a model of what's going on. And that's the structural approach. Okay? So that's one point I want to make about this example. The second point I want to make is I'm making structural models sound awfully powerful and good, right? Now, it could be awfully powerful and good. The answer is it could be awfully powerful and good if your model is good. Okay? It's that simple. The power of structural model comes from what? Comes from the power of the theory model. If your theory model is really good, like in this case, if your model really describes the auction data, like really describe how people bid, then you do structural econometrics, it's going to give you a very good prediction, like we just saw. But if your model is bad, if this model doesn't really describe people's bidding behavior, if in reality when people bid, they don't really optimize like our model says, then in other words, if the model is trash, then your prediction is trash. Okay? So how good a structural model is depends on how confident you are in the economic model you really have. And that's the drawback. That's the limitation of structural econometrics, in the sense that in economics, much of a theory is not very good, right? Especially compared with science, natural science. So think about what physicists do. In physics, everybody is structural econometrics. Structural people. Because in physics, everybody trusts their model, right? Their quantum mechanics model, their relativity model. So when they fit their data, they always use their model to fit the data. They very seldomly ever do like reduced form, like linear, quadratic. They never do that, right? They use their quantum mechanics model because they believe in that model. In economics, unfortunately, our model is not that great. So oftentimes when you do structural, your result is not reliable either. That's why these two schools have been fighting forever, okay? People who believe in reduced form thinks that structural people have too much faith in economic models, which are not warranted. Two unrealistic assumptions. The structural people think the reduced form people, their approach is not scientific enough, it's not based on economic models, and it don't generalize well. Okay, do not really extrapolate very well, like we just described. Okay, so these two schools have been fighting, and like I said in this course, I'm going to give you a more detailed overview and tell you how to think about them in a coherent and unified way. Now, this is a second example, right? And then the last example for structural, I'm going to talk about. Am I running out of time? I am running out of time, but I'm going to try to finish this within 5 minutes. I'm sorry about that. Looks like I cannot finish within 5 minutes. You know what? Because we finished 10 minutes early, right? I think let's finish today. I'll do this example next week. Give it time for Justin. Okay. All right. So let's finish today. We'll continue. Sorry, not next week. Thursday. We still have a class on Thursday, right? Okay. Yeah. So let's meet on Thursday again.